podcast. The show where we take complex topics and break them down.
And sometimes build them back up.
Yeah, that's true. Today, we're taking a deep dive into the world of data structures.
Which, as you know, are those super clever ways computers organize information.
To make everything run smoothly. I think a good place to start is with a question for our listeners.
I like where this is going.
Okay, so think about this. Have you ever wondered how your computer finds a file buried deep in your folders? Or how Google Maps figures out the fastest way to get you home without driving you in circles? It all comes down to data structures.
These behind-the-scenes heroes are quietly powering so much of our digital world.
Exactly. So let's unpack this a bit.
Let's do it.
Our source material kicks things off by talking about containers and dictionaries.
Ah, yes, the classic container versus dictionary debate.
Well, the source says that containers are like a simple box holding information.
Right.
And dictionaries use keys to find specific values, kind of like a well-organized photo album with labels. But isn't a photo album also a container?
You're totally right. A photo album is a container, but it's also a dictionary. And that's because it uses labels, those keys, to help you find specific photos.
I see. So it's not just about holding the information, it's about how you access it.
Exactly. A container is like rummaging through a junk drawer. You have to look at everything to find what you need.
Right.
But a dictionary is more like using a library card catalog. You go straight to the card with the right title, and boom, you found your book.
Okay, so efficiency is key when it comes to data structures.
Absolutely. The right data structure can make a huge difference in how fast and smoothly your program runs.
And speaking of efficiency, the source mentions that arrays are like the workhorses of data structures.
They're definitely a go-to for a lot of tasks. An array is basically a collection of items stored in a specific order in memory.
Like a neat row of houses, each with its own address.
Perfect analogy. That's why accessing any element in an array is so fast, you just go directly to the address you need.
Makes sense. But what happens when you run out of space in your array? Like if you need to add more data?
That's where things get a little more interesting. Traditional arrays have a fixed size, which can be a bit of a limitation.
So you're stuck with the number of houses you started with?
Unless you build an extension, and that's essentially what dynamic arrays do.
They grow as you need them.
Exactly. It's like having a magical row of houses that can expand automatically when more people move in.
Sounds pretty convenient. But wouldn't all that expanding take a lot of time?
It can sometimes, but that's where the concept of amortized efficiency comes into play.
Amortized efficiency. Sounds complicated.
It's actually a pretty simple idea. Think of it this way. Occasionally, you might have a longer wait while the houses rearrange themselves to make room for new residents.
Okay.
But on average, adding a new resident is still super quick. It's all about balancing those occasional slowdowns with the overall efficiency of the structure.
This is really making a lot of sense. Now, the source then goes on to talk about linked lists.
Linked lists. These are a bit different from arrays.
It says they're chains of nodes, each node containing data and a pointer to the next node.
Right. Imagine it like a scavenger hunt, where each clue leads you to the next one.
Okay, I can see that.
Linked lists are super flexible. You can keep adding nodes to the chain as needed.
And they're easy to insert or delete elements once you find the right spot in the chain.
Exactly. But finding that spot can sometimes be a bit slower than with arrays.
The source mentions that searching a linked list can be slower than an array. Why is that?
Well, remember how we talked about arrays being like houses with addresses? With a linked list, it's more like following a winding path through a forest.
Okay, I see.
You have to go from one node to the next, following the pointers until you find what you're looking for. There's no direct route like there is with an array.
So it's like taking the scenic route versus the highway. Sometimes the scenic route is nice, but if you're in a hurry.
Exactly. Now, speaking of journeys, if you're enjoying this deep dive through data structures, make sure you're following Explained for more fascinating explorations.
Great reminder.
So where were we? Ah, yes. Linked lists those meandering paths of data.
Right. The source then jumps to stacks and queues, two structures where the order of things is super important.
You could say that these structures are all about how you add and remove items.
It makes me think about planning a road trip.
Okay, how so?
Well, you pack your car in a certain order, right? Suitcase first, then camping gear, then snacks on top.
I see where you're going with this.
And when you get to your destination, you have to unpack in reverse order, snacks first, then camping gear, then suitcase.
That's a stack. Last in, first out.
Exactly. And a queue is more like waiting in line at a popular restaurant.
First come, first served.
Precisely.
Yeah.
It seems so simple, But the source emphasizes how important these structures are.
They're essential for all sorts of tasks. Think about managing tasks on your computer or processing requests on a web server.
I'm starting to see how these seemingly simple concepts can be so powerful.
They really are the building blocks for so much of what we do with computers. And here's the really cool part. Both stacks and queues can be implemented using either arrays or linked lists.
It's like you can choose the underlying structure based on the specific needs of your program.
Exactly. It's all about selecting the right tool for the job.
And speaking of tools, things start to get a bit more tree-like with the next structure, wouldn't you say?
You could say that. Trees introduce a whole new level of complexity.
The source describes them as having a hierarchical structure with a root node and branches leading to child nodes and so on.
Right. It's like a family tree. You have grandparents at the top, then parents, then children.
I'm getting a much clearer picture now. But are all trees structured like a family tree?
There are actually many different types of trees, each with its own unique properties and applications. Oh, yeah. Some trees are optimized for storing data efficiently, others for making decisions in a game, and some even power search engines by organizing massive amounts of website data.
Wow. So it's like the tree concept can be adapted to solve a wide variety of problems.
Exactly. And that's what makes them so powerful.
The source mentions something called tree traversal. Different ways to systematically visit every node in a tree?
Ah, yes. Tree traversal is all about exploring the tree in a specific order, visiting each node, and performing some operation on it.
So is it like choosing a route through that family tree, visiting each relative in a particular order?
That's a great analogy. There are different traversal methods, each with its own advantages depending on what you're trying to achieve.
I can see how navigating these branching structures could get pretty complex. And then the source throws another curveball into the mix.
Yeah.
Recursion.
Recursion. One of my favorite topics.
It always makes me feel like I'm going down a rabbit hole.
I know what you mean. It can be a bit mind-bending at first, but it's a super elegant and powerful technique once you grasp it.
The source compares it to those Russian nesting dolls, where each doll contains a smaller version of itself.
Perfect analogy. That's essentially what recursion is, a function calling itself to solve smaller, self-similar problems.
So it's like breaking down a big task into mini versions of the original task.
Exactly. And this can lead to really clean and concise code for certain types of problems.
But there's a catch, right? The source mentions that recursion can sometimes be tricky to get right and might use up a lot of memory.
You're right. Like any powerful tool, it needs to be used wisely.
So understanding when to use recursion and when to stick with other approaches is key.
Absolutely. And that comes with experience and practice.
Okay, this is all starting to click now. The last structure the source covers is graphs.
Ah, graphs. These are where things get really interesting.
It describes them as sets of nodes connected by edges. It makes me think of those social network maps with people as nodes and connections as edges.
You're on the right track. Graphs are incredibly versatile. They can represent relationships, networks, maps, pretty much anything you can visualize as interconnected points.
So like the internet itself is a giant graph.
Exactly. Or think about transportation systems, roads, connecting cities, flight paths between airports. It's all graphs.
That's amazing. And speaking of connections, I'm curious to hear from our listeners. What are some everyday examples of data structures that you can think of?
Great question.
Drop your ideas in the comments.
Yeah.
We love hearing your real-world connections.
I can't wait to see what people come up with.
So we've covered a lot of ground here, from containers and dictionaries to arrays and linked lists, from stacks and queues to trees and graphs. It's been quite a journey.
And we're just getting started. There's so much more to explore in the world of data structures and how they shape the digital landscape we navigate every day.
I'm excited to keep learning. But for now, I think it's time to take a break and let our listeners digest all this information.
Great idea. We'll be back soon with more insights and explanations.
Until then, happy coding.
And happy exploring. All right, so where were we? Yes, graph those fascinating networks of nodes and edges.
Right, and I think the source material wants to dive a bit deeper into how those graphs are actually stored in a computer's memory.
That's a great next step, because remember, it's not enough just to have the concept of a graph. You have to actually represent it in a way that a computer can understand and work with.
And the source mentions two main approaches for doing this: adjacency matrices and adjacency lists.
Those sound a bit like secret code names. Can you break those down for me?
Well, I think I can with the help of our trusty source material. So imagine you're organizing a party.
A party. I like where this is going.
And you want to keep track of who knows whom. You could create a big chart
Okay.
like a spreadsheet where each row and column represents a guest.
I'm visualizing this.
Each cell on the chart would indicate whether those two guests know each other.
Got it. So, like, if guest A knows guest B, you'd put a check mark in the cell where their row and column meet.
Exactly. And if
Yeah.
they don't know each other, the cell would stay empty.
So this chart, this matrix, is essentially a snapshot of the relationships in our party network.
That's right. It's called an adjacency matrix.
Yeah.
And it's a super visual way to see the connections.
I can see how that would be useful. But the source also mentions a potential drawback.
Yeah, it can be a bit memory intensive,
Yeah.
especially for large networks where not everyone knows each other.
It's like having a giant phone book where everyone's listed even if they've never met. Not very efficient.
Exactly. That's where adjacency lists come in. They offer a more streamlined approach.
More streamlined. How so?
Well, instead of one giant chart for everyone, we create separate lists of connections for each person.
Ah, so it's like everyone having their own personal contact list instead of one massive directory.
Exactly. Each guest would have their own list containing only the people they know directly. It's a much more efficient way to store those connections, especially for large, sparse networks.
This is making a lot more sense. So we have adjacency matrices, which are great for visualization but can be memory hogs. And then we have adjacency lists, which are more efficient for storage but maybe not as visually intuitive.
It seems like with data structures, it's often about trade-offs.
Absolutely. Choosing the right structure depends on the specific problem you're trying to solve and the constraints you're working with.
Now that we have a better understanding of how graphs are stored, let's talk about what we can actually do with them.
Ah, yes. The fun part. Graphs are incredibly powerful tools for all sorts of applications.
The source material highlights a few examples, like finding the shortest path between 2 points, identifying clusters of friends with shared interests, or even recommending connections on a social network.
These tasks might seem unrelated, but they all rely on the underlying structure of the graph.
And to perform these tasks, we need algorithms.
Algorithms are like sets of instructions that tell the computer how to navigate the graph and extract meaningful information from it.
So they're like special recipes for working with graphs.
Exactly. And just like with recipes, there are many different graph algorithms, each designed for a specific purpose.
This is starting to feel like a whole new world opening up. It's amazing to think about all the complex calculations happening behind the scenes every time we use a navigation app or get a friend suggestion on social media.
It really is. And it all boils down to understanding how to organize and manipulate information effectively using the right data structures and algorithms. This is all starting to click for me. But I have to admit, the concept of recursion still feels a bit like a puzzle I'm trying to solve.
Don't worry, you're not alone. Recursion can be a bit of a head-scratcher at first, but it's a powerful tool once you grasp the underlying principle.
Our source material uses the analogy of those Russian nesting dolls. Could you walk me through how that analogy works in practice?
Okay, so imagine you're trying to write a program to calculate the factorial of a number.
The factorial. Remind me what that is again.
It's the product of all the positive integers less than or equal to a given number. So for example, the factorial of 5 is 54321, which equals 120.
Got it. So how does recursion help us calculate that? Well, imagine you have a function called factorial that takes a number as input. If the input is 1, it simply returns 1. But if the input is greater than 1, it returns the input number multiplied by the factorial of the input number minus 1.
Wait a minute, so the function is calling itself?
Exactly. That's the heart of recursion. It's a function that calls itself to solve a smaller version of the same problem.
It's like opening one of those nesting dolls and finding a smaller doll inside, which contains an even smaller doll, and so on.
That's a perfect analogy. Each time the function calls itself, it's like opening another doll until you get to the smallest doll in the center, which in our case is the factorial of 1.
And then you work your way back up, multiplying the results as you go.
Precisely. Each function call gets added to something called the call stack. And as each call completes, it's popped off the stack until you get back to the original call with the final result.
Okay, that's starting to make more sense. But our source material also mentions that recursion can sometimes be less efficient than using loops. Why is that?
It comes down to overhead. Each time a function is called, the computer needs to store information about its current state. This storage and retrieval process adds a bit of overhead compared to a simple loop, which just iterates through a set of instructions.
So it's like taking a detour every time you make a recursive call, whereas a loop is like staying on the main road.
That's a helpful way to think about it. Recursion can be elegant and make your code more readable for certain problems, but it's not always the most efficient solution.
So as with many things in programming, it's all about choosing the right tool for the job.
Exactly. And understanding the trade-offs involved. Now, if you're enjoying this deep dive into the world of data structures, make sure you're following Explained for more insights and explanations.
We'll be back with the third and final part of our data structures deep dive after a short break.
Welcome back to our deep dive into data structures. I hope you're ready for more because we've got some fascinating territory to cover.
I'm definitely ready. In the previous parts, we explored all sorts of structures like arrays, linked lists, trees, graphs. It's been quite a journey.
It has. And now we're going to shift gears a bit and talk about how these seemingly abstract concepts actually manifest in our daily lives.
The source material calls this the real-world relevance of data structures, and I'm super curious to hear your take on this.
Well, I think it's important to remember that data structures aren't just theoretical constructs. They're the foundation for countless applications and technologies that we use every day.
So it's like they're working behind the scenes, shaping our digital world without us even realizing it.
Exactly. Take something as simple as searching for information online. Every time you type a query into a search engine, a complex interplay of data structures and algorithms kicks into gear.
So the search engine isn't just magically finding what I'm looking for. There's some serious computational power at work.
Absolutely. It's using a carefully crafted index built from massive amounts of data organized using structures like trees and graphs. This index allows the search engine to quickly narrow down the possibilities and deliver relevant results in a fraction of a second.
That's incredible. I never realized how much thought and complexity goes into something we take for granted every day.
And that's just one example. Think about social media platforms recommending friends or products based on your connections and interests, or navigation apps guiding you through traffic using real-time data and sophisticated algorithms.
It's all starting to make sense now. Data structures aren't just abstract concepts. They're the building blocks for the digital world we live in.
Precisely. And understanding these building blocks can give us a deeper appreciation for the power and potential of technology.
The source material raises an interesting question here. It asks, what are some everyday examples of data structures that our listeners can relate to?
That is a good one. I think a really simple example would be a playlist on your music app.
Okay, how is that a data structure?
Well, it's a linear structure, a sequence of songs arranged in a particular order, kind of like a linked list.
Right, and you can add or remove songs from the playlist, which is similar to inserting or deleting nodes in a linked list.
Exactly. And then when you play the playlist, the music app uses an algorithm to traverse the list playing each song in order.
So even something as simple as listening to music involves data structures and algorithms. That's pretty cool.
It is. And as we become more aware of these underlying concepts, we can start to see them everywhere.
Absolutely. Now, the source material takes a turn towards something that seems a bit more philosophical. It talks about the relationship between data structures and the real world. How do these abstract concepts actually manifest in our daily lives?
That's a fantastic question, and it gets to the heart of why data structures are so important. They're not just theoretical constructs, they're the foundation for countless applications and technologies that we use every day.
So it's like those invisible forces shaping our world that we rarely stop to think about.
Exactly. Take something as simple as searching for information online. Every time you type a query into a search engine, a complex interplay of data structures and algorithms kicks into gear.
So the search engine isn't just magically finding what I'm looking for.
Not quite. It's using a carefully crafted index built from massive amounts of data organized using structures like trees and graphs. This index allows the search engine to quickly narrow down the possibilities and deliver relevant results in a fraction of a second.
That's incredible. I never realized how much thought and complexity goes into something we take for granted every day.
And that's just one example. Think about social media platforms recommending friends or products based on your connections and interests, or navigation apps guiding you through traffic using real-time data and sophisticated algorithms.
It's all starting to make sense now. Data structures aren't just abstract concepts. They're the building blocks for the digital world we live in.
Precisely. And understanding these building blocks can give us a deeper appreciation for the power and potential of technology.
So the next time I'm scrolling through my social media feed or using a navigation app, I'll have a whole new perspective on what's happening behind the scenes.
That's the goal, to spark curiosity and empower people to see the world through a different lens.
This deep dive has been so eye-opening. We've gone from the basics of arrays and linked lists to the complexities of graphs and algorithms, and we've even explored how these concepts are shaping the world around us.
It's been a truly fascinating journey. And if you've enjoyed this exploration with Explained, don't forget to subscribe for more insightful deep dives into the topics that matter.
We're always looking for new challenges and questions to tackle. So if you have any suggestions for future episodes, let us know. We love hearing from our listeners.
Absolutely. Until next time, keep those curious minds engaged and never stop exploring.
Happy learning, everyone!